Okay, so this is the first example. We are going to calculate the U value. First, we have to calculate the R value, and finally, we will calculate the U value of this wall. We have brick 4 inches, concrete masonry unit 4 inches, extruded polystyrene or foam or polymer. This is thermal insulation 6 inches, and this is the internal finish, the drywall. So we have to use the Excel file. So this is one of your Excel files. Some of you have submitted this, and I'm using this as a, yeah, so this is what you were supposed to have done by today. And this is one of your Excel files. I don't know who this is, I don't know. Anyway, here we have the walls. You remember that first we need this coefficient, HI. This is the interior convection coefficient, which is 1.6. In walls, it's always the same. This is the exterior convection coefficient. It's 2.93. The first layer is this one. So the thermal resistance of this exterior layer, we don't have any solid element. So we don't have thermal conductivity and we don't have any thickness. What do we have? We have the thermal resistance. So the thermal resistance, if I double click here, is 1 divided by HE. So this is the first thermal resistance. The last one, if I click here, that would be 1 divided by HI. Okay. And then in the middle, I have different materials. I told you to go over that table, and you had to include here 13 different materials. Okay, I will use this as a, I'm going to copy, right click, copy, and then I click here, right click again, and insert copy cells. Like this. Why I'm doing this? Because I'm going to generate different walls. That will be wall 1. Okay, and now I'm going to insert, or I'm going to delete some of these layers I have here. So now I move this here and there. So this is the first wall we are going to calculate. So first, air out. This is it. So it's 0.34, and it will always be 0.34. This is 1 over 2.93. Okay, so this is always the first layer. The second layer, in this case, we have brick. Okay, so here we have brick. The thickness is 4 inches. And we need the thermal conductivity of bricks. Where can we find the thermal conductivity? So we have to find thermal conductivity on the previous lesson, which is courses, lesson. It's in lesson 3. Yeah, there you go. Okay, so this is lesson 3, and this is the thermal conductivity. So we know that thermal conductivity is 5 BTU, inches, hours, Fahrenheit, feet square. Do we have units here? Yes, it's BTU, inches, hour, R or F. These are Fahrenheit degrees, feet square. So this is 5, and the thickness, sorry, it's 4. So I click here, and the formula should be thickness 4, which is the 35, divided by the thermal conductivity, C35. It is C35. Okay, so it's correct. Then, what is the second? The second layer. So this is the first layer, 4 inches, brick, 4 inches, thermal conductivity 5. The second layer, concrete masonry unit. Okay, so here we have to type a concrete masonry unit. So the concrete masonry unit, the thickness now is 4. Okay, 4 inches. What is the thermal conductivity of the concrete masonry unit? Okay, let's go to that table. And here we have concrete blocks. Okay, so it's not a concrete block, concrete masonry unit, it's the same. So here we have a 4-inch concrete block. And what happens? We don't have a thermal conductivity here. So if we don't have a thermal conductivity, we have to go all the way, because here we have the thermal resistance. And the thermal resistance of a 4-inch concrete block is 0.8. Okay, so here we don't have thermal conductivity, so we can delete this because we don't have a thermal conductivity. And here we can type directly 0.8. It's the same as the brick, but it doesn't have to be the same. Okay, so in this table, when we don't have thermal conductivity, we cannot apply the formula we applied here, thickness divided thermal conductivity. We have to, if we have a 4-inch, so here we have a 4-inch concrete masonry unit. So in this table, we have a 4-inch concrete masonry unit. We have to go directly to this column, to this thermal resistance. So that would be 0.8. So this is what I have typed here, 0.8. Sorry, this one. Okay, so this is blank because in that table, this value, we don't have a value for thermal conductivity. Okay, what's next? We have the EPS, the extruded polystyrene, which is 6 inches. Okay, so we have to go to that table. And where is the extruded polystyrene? It's here. This is the extruded polystyrene. And again, do we have a value for the thermal conductivity? We don't. So what do we have to do? We have to go to the thermal, I will expand this. So we have to go to the thermal resistance. But do we have here 6 inches of thermal conductivity? We don't have 6 inches. When we are analyzing concrete blocks, here we have 4 inches. So I have to take this value directly. But in this thermal insulation, in the extruded polystyrene, this is 3/4, this is 1, and this is 1.5. Okay, so the easiest way is if I know the thermal resistance of 1 inch, 5, what is the thermal resistance of 6 inches? It will be 30. It will be 6 times 5. Okay, I have the thermal resistance of 1 inch of this extruded polystyrene. 1 inch, 5. This 6 inches, 30. So I have to type here, that would be extruded polystyrene. This is blank. We don't have a thermal conductivity. The thickness is 6 inches. And this value is 30. Okay. Finally, the last element is the drywall. So do we have drywall? We have the drywall here. And we do have a drywall. This is 1/2 inch. We don't have thermal conductivity, but we do have thermal resistance, 0.45. 1/2 inch, 0.45. Okay, so now we go back to the Excel file. This is drywall. We don't have thermal conductivity. The thickness is 1/2 inch, 0.5, and this value is 0.45. There you go. Do we have anything else on that wall? We don't. There are 1, 2, 3, 4 solid layers, and we have these 2 air layers, the outdoor and the indoor air layers. So I expand the Excel file now. And as you can see here, we have the interior layer. So you can select all these elements. You can right click here, delete, and there you go. Okay, so we have the exterior layer, the brick, concrete masonry unit, extruded polystyrene, drywall, and interior layer. And now this, okay, so I'll do it again. We can say that this is, we click here, this function. This is the sum. And now I select all this column, accept, and this is the total. Okay, so this is the sum of all these values. And finally, the thermal transmittance. This is better. Okay. So the thermal transmittance, we can't calculate thermal transmittance of each layer. We have to calculate the total thermal transmittance. So that is equals 1 divided by the total thermal resistance. There you go, 0.03. Okay, so this is wall 1. What can you do? If you are, if I upload an Excel, a PowerPoint file, you can either submit the Excel file. Okay, so for this assignment, you can submit the Excel file with wall 1, 2, and 3. And but if you are working with an exam, or if you are preparing a report, you can copy this table, and then you can insert this on the PowerPoint. So you click here, that's a blank page, you paste, and you have this format. So here you can select, if you select this image, you copy this exactly the same image or the same format that you have been working with in the Excel file. Okay, so that would be the solution. So you have here the definition of the wall, and here you have the total, the thermal resistance, and the thermal transmittance of wall 1. So this is example 1, or you can call it wall 1. And this is wall 1. Then you have to complete wall 2. If you see, it's the same. So we have a 4-inch brick, 4-inch concrete block. The thermal insulation is different. We don't have extruded polystyrene. We have a fiberglass. The drywall is the same. Example 3, it's the same, but with fiberboard. Okay, so I want you to understand the difference between thermal resistances with 3 different thermal insulations. So that's why the first one is extruded polystyrene, the second one is fiberglass, the third one is fiberboard. Okay, the wall is the same. The only thing that changes is the thermal conductivity or the thermal resistance of the thermal insulation. And this is the final one. This is a different example. We have an 8-inch concrete block. We have a 12-inch fiberboard, and then we have drywall. Okay, so at the end, what do you have to submit? You have to submit a table like that with 4 different walls. If you click on this Excel file, we can copy. Once we have done this, we just copy, click here, paste, and that would be wall 2. And now you have to change. This is not EPS. This is fiberboard, no, fiberglass, sorry. The thickness is 6, but you have to find the value of this thermal resistance, not 30 anymore. You have to change this value, and then this will change, and that will change immediately. Any questions? No questions?
Nope.
Have you submitted something? I mean, I can always control what you have done.
I submitted something, but after you going over that, I don't think I did the entire thing correctly.
Okay, no, but I can see that this assignment, yeah, there are plenty of submissions. Okay, so after this lesson, you have time. By the way, if you submit something on Canvas, you can always upload it again. Okay, so if you think that what you have submitted is wrong, just submit a second time, a second file. So there are unlimited submissions for this. So if you think that you can make it better and you want to improve your grade, you can always submit another version of the same assignment. Okay, so don't think that, okay, I've done this and it's wrong. What can I do? You can submit it again. So if after this lesson you think that you can improve this, or you can make something different, or you have made a mistake, you can do it again. We have a limit, and the limit is today at midnight. Okay, so if you have submitted something and if you realize that it's wrong, fix it and submit it again, and I will review the last version because I can see all the versions that you have submitted, so I will take the last one. Okay, so that's why we are working with this. So the first assignment was this one. So you had like different materials. You had to work with the thermal conductivity, the thickness, and then you have to calculate the thermal resistance. But I want you to become familiar with this table because some materials, we don't have thermal conductivity. You have to type directly the thermal resistance. And there are other materials, we don't have the thermal resistance of our thickness. So we have to calculate. So if we have the 1 inch board, and this is this value, we have to multiply this value times the actual thickness of our board. So there are 3 ways to get the thermal resistance of a material. If we have the thermal conductivity, it's width or thickness divided by the thermal conductivity. If we have the right size here, it's 4 inch, so we just type this. And if we don't have the right size here, and if we have only 1 inch, so then we have to multiply this value, the 1 inch value, times the number of inches that we have in this material. So there are 3 ways to calculate the same. It might be a little confusing at the beginning, so that's why you have to practice. Okay, so nobody knows this. We have to practice. And there's another thing. We have to understand if this wall has a good performance or doesn't have a good performance. So if I ask you now, what is okay, so do you think this is a good performance? If I have a wall with a thermal resistance R equals 33, do you think it's good or it's bad, or it depends? What do you think? Please do not speak all at once. So someone, what do you think? 33, is it good enough, or it should be higher or lower, or what do you think?
I have no clue.
Just say something. Just say, I think it should be higher. You don't know.
I think it's good, but could be higher.
Why?
Because you said 50 is a good number before.
Perfect. That's
And
the
it
basic. Yeah.
It is better than the other walls that we did.
Yes, sure. So 33, it's better than other walls because I think on Monday we made a few exercises and the R value was really low. It was 4 or 5. Okay, so this is very bad. 33, it's getting better. But well, you have said that I told you that 50 is a good value. It's not that I say that 50 is a good value. It's because of because now we are aiming to design zero energy buildings or high performance buildings. I talked about this on Monday, and I always refer to that website, the Passive House Institute of the United States. There you go. Okay, so what is the Passive House Institute of the United States? Well, they are working with the Passive House standards. Passive House standards, it's something voluntary, so it's not mandatory yet. Probably in a few years, it will be mandatory, especially for the Northeast of the United States. We will have to abide by this Passive House standard. And what is this? What is a passive building? So a passive building, we have to click on Passive House Principles and certification. Okay, so this frequently asked questions. If you're looking up on the internet and you see this FAQ website or site, go there because most of your questions will be solved there. So we had this sample R values guidelines, okay? And so here we have these two asterisks. So these are generated from Passive House Institute of the United States, 2015 studies. Okay, so this came into effect, or they posted these values in 2015. They haven't changed those values because things don't change in building science. I mean, if something is good in 2015, it will be good now. And here, for walls in different areas of the world, of the United States, sorry, here we have Burlington, Vermont. Okay, so in walls, the R value should be between 39 and 51. I told you 50 is a good value because 50 goes well even here in Minnesota, that it's colder than in Vermont or New Hampshire. It's not good in Alaska because in Alaska we need 90, okay? But if you are working with a 50 R value, if you remember that number, it will be good because this is a recommendation. If it's higher in Miami or in Hawaii, okay, so it's not cold there, so there are not a lot of heat losses. So we can have a lower R value from 19 to 27. But if you have 50, that's good. Okay, don't worry. But in cold countries, 50 is kind of mandatory. Okay, so we shouldn't have less than 50. If we had 60, it's even better. But 50 is good enough. So yes, the question is, because I said that 50 is a good value, but it's not because I say that. It's because there's a standard, and there's a standard that applies to the United States and in Northern Europe, where cold is an issue. And in that standard, they mentioned that 50 is a good value. Okay. Again, you have to rely on different sources. If you look up on the internet about R values, you will find, I don't know, a lot of things. But what can we rely on? this is my task here. So I'm letting you know what sites are reliable or are trustworthy, and there are others that are not. Okay, so I rely on the Passive House Institute of the United States. Yeah. Another reliable institution is the Department of Energy. Okay, the Department of Energy, it's not just for buildings. If you want to know anything about energies, if you want to know anything about renewable energy or low greenhouse gas emissions energy, then or clean energy, then we have to access this website, because this is unofficial. This is from the government of the United States. Can we rely on the government of the United States? Yes, let's say that we can rely. We can. I mean, so we have energy sources. We have clean energy. We have energy efficiency. This is not only for buildings. There are a lot of aspects here: energy production, energy distribution. But if we want to know sources of clean energy, we have solar, we have wind, we have water, we have geothermal, biofuels or bioenergy. Nuclear is considered as a clean energy, and hydrogen is considered as a clean energy. Okay, so if you have to find data, because sometimes we don't know what to do, so we have a problem and we need to answer that question, or we have to provide a solution to that problem, and we need data. So what can we rely on? Passive House Institutes. Okay, what is the recommended R value? If I'm designing a house in Jacksonville, Florida, what would be a good R value for walls? Around 20, 25 is good. Okay, because and you should be able to give this citation. So we need, okay, so I have taken this value from this institution or from this website. We are going to work basically with three kind of institutions or websites: the Passive House Institute, the Department of Energy, and the last one will be the ASHRAE. Okay, so the ASHRAE is, what is ASHRAE? The ASHRAE is the American, it's the American Society of Heating, Refrigerating, and Air Conditioning Engineers. Okay, so there are a lot of recommendations about, ASHRAE is related to energy in buildings, not only to walls. Passive House Institute is related to construction elements. The ASHRAE includes equipment and mechanical systems. And then the Department of Energy, it includes everything. It includes the energy generation, the energy transport, the energy distribution. So it's broader. Okay, but these three websites, we don't have to memorize anything, because now we can access those websites. But all the answers to our questions will be here in one of these websites. If we are talking about buildings, the Passive House Institute is the one that we have to. If we are talking about equipment, we can access ASHRAE. If we are talking about CO2 emissions, energy efficiency, what kind of energy sources we can work with, the Department of Energy is the right one. So I think I mentioned this last week, and I don't mind repeating myself, because this is very important. Passive House Institute, Department of Energy, ASHRAE. Okay, so 33, it's good for Florida, but it's not good for New Hampshire or Vermont. Another question would be, what do you have to do on this assignment? You have to copy and you have to calculate wall 1, wall 2, 3, and 4. Okay, so you have something, you have a problem, and now you have to calculate the U value or the R value, and then the U value of 4 different walls. But I can ask you a different question. What if I tell you, okay, what do I have to do? if I want an R value, I want to increase this, I want this to be 50. What can we do? You don't have to increase the thickness of brick. Imagine that, okay, so I have 4 inches, so let's work with 8 inches. Does it change? No, still 33. Okay, concrete masonry unit, 4 inches. Now let's say 12. It doesn't change. So what matters here? The thickness of the thermal insulation. So you remember that the R value of thermal insulation was 5, sorry. The thickness was 6, so 6 times 5 equals 30. So imagine that you double the thermal insulation. So that would be 12 inches. So that will be 60, because it would be 12 times 5. And now this total value is 63. It's above 50. Okay, so if we want to improve the performance of the wall, and improving the performance of the walls means that we have to be with a thermal resistance above 50. What do we have to do? We always have to increase the thickness of the thermal insulation. That's the answer. So don't work with the brick, with the concrete masonry unit. No. Just work with the thermal insulation layer and increase that thermal insulation. And this is what we have to do. Okay, so the answer to this is very simple. We can have a table, but now after 25 years of working as an architect, I don't have to calculate anything. Why? Because I have internalized dimensions. And if I'm designing a wall, I know that I need at least 10 inches. 6 inches is not enough in New Hampshire. I know that. Okay, so 10 is enough, and it's very easy to remember. 10 inches, R value above 50. So just by remembering these two figures, we are safe. And even if we don't have an Excel file, if we don't have a calculator, I know that I have this. If I design a wall with a 10-inch thermal insulation, it's more than enough for New Hampshire. If I'm in Alaska, probably it will be 20 inches. Okay, so that's the goal of this course. You are young, you're still young, so you can be grateful. But you don't have experience, so that's why you have to do this many times. So this on this course, we will calculate hundreds or thousands of walls, roofs. So we will do this many times. Okay, so there will be different materials, and then you have to work with this Excel file. After 1,000 times calculating these kind of things, then you don't have to calculate anything. You internalize the values, and then you can design a good wall without calculating anything. So, but that comes with experience and with time. So we are starting our journey here about the building science, but in 10 or 20 years, I'm sure that we'll be at my level or even above. Okay, so this is it. Now remember that you have to work with the assignment. You have to open the assignment and you have to calculate 1, 2, 3, 4 different walls. And well, I don't think we will have. Well, here we have a 12-inch fiber board. Probably this one would be above 50. I don't know, because this is fiber board. I don't know. I haven't calculated that. But most likely those two walls here, the total R value won't be above 50. And let's see the fourth one and see what happens. Okay, so this is the wall. You remember that last week we were talking about your warm-up assignment, the window. And I told you that you had to analyze dimensions. I needed to know the dimensions of the window, and I needed to know the dimensions of the wall where that window is placed. Because today we're going to use that, and we are going to talk about thermal loads. Okay, so thermal loads are related to the U value, the thermal transmittance. And there's a formula, there's a very simple formula that comes from the Fourier law. We explained the Fourier law last week. It seemed like 2 years ago, but no, we explained Fourier's law last week. So that law states that Q, which is the thermal load, equals the U value, the thermal transmittance, times the surface area times indoor temperature minus outdoor temperature. Okay, so this is the thermal load. At this point, we know how to calculate the U value. Okay, so if we are analyzing the thermal load of this wall, the U value, the thermal transmittance, it's 0.03. Okay, what about the area? So the area, imagine that you are working with a wall. So this is a wall, and you are working with a window. This is your window here, like this. Okay, and we have dimensions now. Let's say that this is okay, imagine that this is 10 feet. Well, a little bit more, let's say 15 feet. And the height is 10 feet. Okay, so this is what I want you to okay, what I want you to do for this warm-up assignment. So we agreed that you showed me the window, but now we need an elevation of that wall, and I need to know the dimensions of that wall, and I need to know the dimensions of the window. So let's say that this window is change the color. Okay, so let's say that that window is 5 feet, and the height is 3 feet. Okay. So this is a very simple elevation. We have a wall and we have a window. So now we have to calculate the thermal loads. First, we need the thermal transmittance. We have already calculated the thermal transmittance of the wall. We need the area. What is the area of that wall? So here we have two different materials. First, we have the area of the window. So we can calculate the area of window. What's the area of window? It's 5 times 3. So this is 15 feet square. This is the area of the window. What is the area of the wall? What's the area of the wall? The area of the wall is the total area, so it's 15 times 10, which is 150 square feet. And then we have to subtract the area of the window, because we are asking for the area of the solid wall. It's not the total area. No, we have the area of the material, which is the window, and then we have the area of the blue material. So it's 15 times 10, 150, minus the area of the window, which is 15. So that would be 135 feet square. Okay. So now what is the thermal load? So the thermal load through the wall equals thermal transmittance. We have calculated thermal transmittance. It's 0.03. So that will be 0.03. What is the area if we are calculating the thermal loads through the wall? What is the area of the wall? The area of the wall is 135 feet square. So this is 135. And finally, we have indoor temperature minus outdoor temperature. Well, this can be something that okay, so we can say that the indoor temperature, by the way, what is, I'm asking you, so I want an answer to that question. What is a good indoor temperature?
70 degrees.
70 degrees, what degrees? Celsius, Kelvin, or what?
Fahrenheit.
Fahrenheit, okay. So this is 70 Fahrenheit. This is a comfort. If you watch the videos, I always use 70 Fahrenheit because this is comfort. And it's comfort in New Hampshire, and it's comfort in China, and it's comfort in the Philippine Islands. I mean, it's comfort everywhere. So 70 Fahrenheit is a temperature at which human beings are comfortable. So our goal is to keep indoor temperature close to 70 Fahrenheit. What about outdoor temperature? I don't know. What do you think is the minimum outdoor temperature that you can have in New Hampshire? In China? What do you think? Silence. I don't know. I have spent 2 winters there, and it's tough. So what is the lowest temperature that we can have in Keene? What do you think? Just make a wild guess.
-3.
-3. Yeah, why not? Do we have negative figures? Well, someday, I mean, when it's really, really cold, we can be below 0 Fahrenheit in New Hampshire. September, it's I want Fahrenheit, by the way. Yeah, so it's around 50 Fahrenheit, and the maximum temperature that we can find in September is around 65 Fahrenheit, or no, 70 Fahrenheit. Yeah, between 60 and 80. Okay, so those are the average temperatures. The average minimum, or the minimum average, and the maximum average temperature. What about in winter, in January? Yeah, definitely we are below 20. Yeah, so probably, I don't know, but we can have a minimum temperature below 0. We can have 0 or -3. But anyway, we can find this information on the internet, but experience matters. So if you have lived there and you know that you can have a temperature below 0, that's fine. Okay. So for the sake of this calculation, we are going to use these two values: 70 Fahrenheit inside and -3 outside. So this is 70 Fahrenheit indoor temperature, and the outdoor temperature, we need brackets because this is -3. Okay, so if we now calculate this, it's 0.03 times 135 times 73. So if I'm not wrong, this is 295.6. This is the thermal load through this wall. Okay, so what is the thermal load? It's the amount of heat that we are losing. So what do we have to do? We have to compensate for the heat that we are losing. And how do we compensate? With the heating system. Okay, so we need a heating system that at least, if we want to compensate the heat losses through the wall, we need at least provide that room with 295 watts. Okay, so units are important here. And so I'm going to open another line. What are the units? Okay, if you look at the U value, the units are BTU, hour, Fahrenheit, feet square. And this is important because if we mistake the units, everything will be wrong. Okay, so the U value, make it smaller. Okay, the units are BTU divided by hour, Fahrenheit, feet square. So those are the units of the thermal transmittance, the U value. Times, what are the units of the surface area? It's feet square. Times, what are the units of temperature? Fahrenheit. Okay, so now we cancel feet square. Because we have feet square here and we have feet square here. We cancel Fahrenheit because we have Fahrenheit here and there. So the final result is BTU divided by hour. Okay, so the units here are BTU divided by hour. So that's the right answer to this. The thermal load through the wall is 295.6 BTU per hour, or BTU hours, or BTU divided by hours, whatever, but it's BTU hour. Okay. So we have learned a lot because now we can analyze, if we know the components of a wall, we can analyze the U value. Using this Excel file, we can analyze the U value. And then with this formula, we can measure the power that we need in our heating system. This is all we need to know. Now we have to do this in real buildings. And there are a lot of walls, there are a lot of materials, and you have to do this many times. But everything that we should learn this course, it's on these 2 slides. We have to learn how to calculate R values and U values, and finally we need to learn how to calculate thermal loads. So we will be doing this over the next 5 or 6 weeks, and we will have different examples, different walls. We will calculate U values, then we will have different measurements, and then we will calculate thermal loads. So that's why I wanted you to measure this, okay? Because now next assignment, I will post the next assignment today. So you have to select one of these walls, one of the walls that you have already calculated. Then you have to calculate the, well, we have already calculated the U value of this wall. And finally, we have to calculate thermal loads. And the only thing you have to, well, we have already calculated this, you have to let me know the area. You will have different areas because you have different walls, different windows, okay? So that's why I need an elevation like that. And now I don't want a perspective of the window. I want an elevation, and on that elevation, you have to let me know the width, the height of the wall, and the width and the height of the window. And then you have to calculate the area of the wall, and you have to calculate the area of the window. Are we done? Not yet, because this is the thermal loads in walls. And now we have to calculate thermal loads in windows. Okay, so the formula is the same. It's the U value of the window times the area of the window times indoor temperature minus outdoor temperature. And what is the U value of the window? Okay, we can't calculate U values of windows. We have to work with catalogs. And working with catalogs, it's something, okay. I have taken these values from catalogs. So here we have the U value in, and it's directly in imperial units. Okay, so this is something we will talk about windows a lot this year. But the first thing is that we can have at least 3 different kinds of windows. We have a single window. It's a glass pane without air chambers here. We can have a double glaze or a double glazing with 2 panes of window with air in the middle. And we can also have triple glazing. Okay, the triple glazing is we have 3 layers of glass. We are not using single windows anymore because no, I don't think they are even legal for buildings. You can use single windows in cars or whatever, but in buildings, single windows are forbidden and they have a very high U value. Okay, so we have to use at least double glazing. So a typical value of a double glazing can be, yeah, from 0.3 to 0.5. This is, yeah, if we are using a double glazing, we can do this. So if we are analyzing thermal loads of windows, we are talking about double glazing. Then the U value of a double glazed window can be between 0.33 and 0.47, let's say 0.4. Get used to working with units, BTU, hour, Fahrenheit, square. Times the area of windows. In our elevation, the area of our window was 15 feet square. Okay, so this is 15 feet square times temperature difference. It's the same. So we were working with 70 minus -3. So we can work with 70 minus -3. Okay, so what is the total thermal load through the window? It's 0.4 times 15 times 73. It's 438. 438 units BTU per hour. Okay, so the thermal load through the wall, it's 295. Thermal load through the window, it's 438. What catches the eye here? That we are losing a lot of heat through the window. Although the area is lower, but we are losing a lot of heat through the window. Why? Because the U value of the window is 0.4. It's the usual U value for windows, 0.4, not bad. But the U value for walls is 0.03, so it's much lower. Why? Because we have a lot of thermal insulation. We don't have thermal insulation through windows. So be careful with windows, because now if we want to calculate the total thermal load, windows and walls, the total thermal load will be the thermal load through the wall smaller plus the thermal load through the window. So total 295.6 plus 438. It's 733.6. 733.6 BTU hour. This is it. I repeat it again. First, we need data. Okay, so what are the data of our problem? We need dimensions. First, we need the dimension of the wall. We need dimensions of the windows. We have to calculate the area of window, and we have to calculate the area of the wall. But be careful, because you have to subtract the area of the window. So we have area of windows, area of walls. We have the indoor temperature, and we have the outdoor temperature. So this is always something that is given. And depending on where we are working, if we're in Florida, probably we won't use -3. I don't know what the minimum temperature in Florida is. I'm sure it's not -3. That indoor temperature is always around 70. So those are the data. So this is the statement of the problem. And now we have to, this is our design. So we have designed this wall with that window. And now we want to assess this design in terms of energy efficiency. What is the goal? We have to reduce the energy, the heat losses that we have through windows, through walls. So we have to calculate the thermal load. So the thermal load through the wall, it's always the same formula. Q stands for thermal load, equals U value times the area, the surface area of the wall, times indoor minus outdoor temperature. So those are our values, 0.03, the U value, 135, the area of the wall, 70 minus -3, the temperature difference. We multiply this, and this is the final result, 2.5 times 6 BTU hours. Units are important. Then we can calculate this in Windows, so we can have a table like this to calculate the thermal transmittance of Windows. We have to go over catalogs. Okay, so I have this catalog, very simple because we have only 1, 2, 3 kinds of windows, and we have simple glazing that we can't use, and we have double glazing. So if this double glazing is 0.47 and this double glazing is 0.33, that would be better for sure, because the lower the U value, the better. Anyway, an average is like 0.4. So imagine that the U value of a window is 0.4. The area of the window was 15 square feet. And the temperature difference is the same, 70 minus -3. This is the thermal load through the window. And then we have the total. The total thermal load would be, well, instead of windows plus walls, I would say walls plus windows. So 295 is the thermal load of the wall. 438 is the thermal load of the window. So the total is 733.6. And that's it. This is, I mean, we have learned something useful today because we are paying for this. So with this value, you can calculate the amount of money that you will have to pay for your next energy bill. It can be gas or electricity or whatever. With this value, you can easily calculate the amount of money that you are going to pay for your heating system. And that's something useful. I mean, it's not like a figure, okay, what's that for? With this figure, then we calculate the money. So over the next few weeks, we will turn BTU hours because those are units of power. We can work with units of energy, but finally we will work with dollars. And everybody understands dollars. Nobody say, okay, $1, is it much or too? Okay, so you don't know if the 700 BTU hours is too much or not, or it's something usual. But if you pay $100, you say $100. You know what this is. I don't know, are you still there? Do you have any questions?
Nope, I'm all set.
What do you have to do now? Well, first, go over the assignment. If you have to submit these again, So remember that you have to calculate 4 walls. And then you have to go to the warm-up assignment. I haven't posted that assignment yet, but some of you asked me, what do I have to do with the measurements? I have the measurements and I have drawn an elevation. So what do I have to do? So now it's time to use that information. You need to provide me with the elevation of this wall. I won't check it. I mean, I won't go there to check whether dimensions are accurate or not. I need a wall with the width and the height, and I need a window or 2 windows or 3 windows placed on this wall with dimensions. And then you have to calculate the area of windows and you have to calculate the area of walls. With the area of windows and the area of walls, you have to calculate thermal loads. First for walls, second for windows. The U value of the wall is the one that you have already calculated with that table. The U value of windows, you can use either 0.47 or 0.33 or something between 0.07 or no, 0.33 or 0.47, so something in the middle. And with this, you have to calculate thermal loads, the U value, the area of the window, and the temperature difference. And finally, you have to add this and that up, and you have to calculate the total thermal load.